Introduced an Atwood machine. The Atwood machine is simply a pulley that has a string resting over top of it, or it could be a rope or a wire, or possibly even a chain of some sort. And then attached to the ends are weights. In this example, you'll see that I have 1 kilogram attached to each side. With the 1 kilogram mass, we can calculate our force of gravity, which was 9.81 newtons on each side because the force of gravity would be equal. Since the object is not resting on a table or a counter or a bench, there are no normal forces. So, what is holding it up is the force of tension. And the force of tension on the 1 kilogram on the left side must equal the downward force, which is caused by gravity. So the force of tension here is 9.81 newtons. When I look on the other side, because it also has a downward force of 9.81 newtons, the force of gravity once again is also 9.81 newtons, the tension in the rope on the other side. And you'll note that the tension is always equal throughout the rope. Let's think about that for a moment. We are making an assumption of a weightless rope or string or whatever we're using. So I've got the same pulley system here with the Atwood machine set up on the right. All I've done is I've just pulled it down so that one of the masses is down low, the other mass is up high, but otherwise the machine is equal. If the rope or string or whatever had mass, then you would be able to see that the right side would be heavier than the left side. And we don't want to have to worry about calculating the weight of the rope and how long is the rope on each side and use that. So it's important that with the Atwood machine, we're going to make the assumption that we have a weightless rope. Similarly, we want to make sure that the pulley involved, we're not calculating any friction in the pulley or any weight in the pulley. So we're going to assume that it's a weightless, frictionless, and all it's doing is just transferring the direction of the force around the pulley. With Atwood machines, there are typically two questions asked. What is the tension in the rope? And what is the acceleration? First off, we need to remember that the tension in the rope is always consistent. It doesn't matter if the masses are the same or different, the tension will be consistent. When the masses are equal, the tension is equal to the force of gravity on each of the masses. So if the gravitational force is 10 newtons on each side, the tension is 10 newtons. If the force of gravity was 50 newtons on each side, then the tension in the string is 50 newtons. And what about the acceleration? Well, if the masses are the same, then the net force all cancel out in our free body diagram. There is no acceleration because according to Newton's first law is that you need something to cause this imbalance to happen. So there is no acceleration. If we go to another scenario where the masses are not equal, remember the tension will be consistent, but we're going to have to calculate this because it is not as simple as the other scenario. And because we have different masses, we will have an acceleration. So the first step will be to complete our free body diagram of this. So the scenario we're going to use is we have one mass is 3 kilograms and the other mass is 2 kilograms. Let's find the force of tension in the rope, and what is the acceleration? I have two masses hanging here of different weights. So what we need to realize, I'm going to draw the free body diagram, is I have a force of tension number one on this side. And I don't know how much it is, but on this side, where I've got the 3 kilogram mass hanging, I have a force of gravity of 29.43 newtons. On the other side, I have a force of tension over here. We'll call that FT2. And I have another force, FG2, of 19.62 newtons. And they were just simply calculated by multiplying the mass times the gravitational pull. I'm using 9.81 meters per second squared. So now what we see is we have on the left side an up and down force, and on the right side we have an up and down force. Remember, the pulley is simply changing the direction of our forces. And there's many ways of doing this, but what I like to do is I like to now draw this a little differently. Since the pulley is simply changing our direction, I'm going to straighten out my rope here for a second. And I'm going to write all my forces in a different way. So in this direction, I had my force of gravity 1, which was 29.43 newtons. Opposing that is my force of tension 1, and it's going in the opposite direction. On the other end of the rope, I have my force of gravity number 2, which was 19.62 newtons, and I had a force of tension number 2 over here. The question is, does this all balance out? Do we end up with a net force of 0? And we don't, because I think it's pretty obvious to see that this entire thing is going to rotate. And the heavier mass here, it's going to rotate in this direction. Okay? So we're going to end up with some kind of net force moving. F net is going to go that direction in this scenario. If the other mass was heavier, it would go the other way. The other thing we need to realize is that this force of tension and this force of tension here are equal and in opposite directions. So they basically cancel each other out. And so our F net in this problem would be equal to 29.43 newtons, take away 19.62 newtons. Now all we have to do is calculate our acceleration using that net force. We know now that our F net in this example will be 9.81 newtons. And yes, that number is convenient, but that was because we were using a mass with a difference of 1 kilogram difference in the mass. Regardless, our F net, we know that F from Newton's second law is mass times acceleration. So I want to return for a quick moment here. What we need to keep in mind is that as this object moves upward, this object is moving downward. And because they are fixed on the rope is not an elastic or a spring. It's not going to stretch or do funny things. If this one moves up a meter, this one moves down a meter, and it does it in the same amount of time. So they are going to have the exact same acceleration. So going back to calculate that acceleration, we would know that F divided by m will equal our acceleration. We know that our force in this example was 9.81 meters per second squared. Divide that, and what is the mass? And this is the point I'm getting at, is it's the total mass. They're both moving together. And because they're moving together, it is the same. In this example, the acceleration would be 1.962 meters per second squared. We have the acceleration. Now, the direction, we have to be very careful of how we define the direction. The acceleration of this side is upward. The acceleration of the other side is downward. It will be equal, but it will be down. Typically, when we talk about, when we do graphing and all those kinds of things, typically this is referred to as a positive direction. This is typically referred to as a negative direction, but I'm going to just use my words to define it clearly. So now that I know my overall acceleration, it's time to figure out the tension. Now, I'm going to just redraw these little diagrams that I have. I have a force of tension on one side, and I had a force of gravity on the same side in the opposite direction. The tension was pulling it up, the gravity was pulling it down. And what we knew that this was 29.43 newtons. This is what we're trying to figure out now. So I'm going to treat this for a moment as a separate piece. And I could have done it with my other one. And I'll do that over here in a minute. Actually, maybe I'll split this down here. So I'll do the other one is the 2 kilograms. It has a force of tension moving upwards and a force of gravity moving downwards. This was 19.62 newtons. Now, we have to keep in mind that our F net for these problems, this one, the F net is bigger than the force of gravity. So what I'm going to do is I'm going to say my F net here would be my FT2 take away my FG2. And I can find the tension over here. Likewise, this one, and that was because this is bigger. This one over here, this one's bigger, so I'm going to say my net force on this side was my FG1 take away my FT1. So what I need to do first is I'm going to find the overall net force acting on just this object. So just this object, my force would be the mass times the overall acceleration. So in this example, what we know is we know that the mass was 3 kilograms and it was accelerating at 1.962 meters per second squared. So from that, we see that we have a force on this side of 5.886 newtons. So that's my overall what's going on this side. I'll do the same thing over here. I could have said, here I have my F is M times A. And so the force on this one is going to be the mass, which was 2 kilograms, multiplied by multiplied by, it was the acceleration, it's not gravity, 2 kilograms times 1.962 meters per second squared, because that's the actual acceleration of the object. So on this side, I end up with 3.924 newtons. So now I can simply calculate my net overall force. So what I have here is using this formula right here, I'm going to say that my F net is the gravity take away the force of tension We know that the F net is 5.886 newtons. We know that the force of gravity was 29.43 newtons. And so a little bit of algebra, I move the 29 over. And I'll end up with negative 23 is the negative FT1. So I'm getting an answer here of 23.544 newtons. That is my tension over here. Likewise, I could have done it on this side. I could say that my F net was, and on this side, it was my, see it, FT2, take away FG2, FT2, take away FG2, 3.924 newtons equals, don't know that number, T2, take away, and what was my gravitational pull? 19.62 newtons. I'm going to take my 19.62 over here, and I'm going to end up with 3.924 plus 19.62, and that will equal my force of tension on that side. And look what I end up with for an answer. I realize I just wrote down a wrong number. This should have been a 3. 29. Yes, I had 23 here and I wrote 24 down below. So this should have been 23.55544. And look at that. I got the same answer on both sides. It just proves that the force of tension on both sides of the string of the Atwood machine is equal. If you're asked to solve this, you don't need to do both. You could do either or. Just pick one and go with it.